This is our work IPoD, selected as highlight poster on CVPR 2024, named as Implicit Field Learning with Point Diffusion for Generalizable 3D Object Reconstruction from Single RGB-D Images. This work is done by CUHK-SZ GapLab and Alibaba Group. IPoD focuses on the task of 3D object reconstruction from single view RGB-D images. Typically in this task, the image depth is used to inversely project pixels in the input image into 3D partial points, and requires to reconstruct the complete shape given the input image and partial points as monocular observations. Besides, the proposed IPoD is a category-agnostic reconstruction model with strong generalizability. To tackle the target task, the state-of-the-art methods MCC and NUMIC develop transformer-based networks to learn an implicit field for reconstruction. These methods learn the implicit field from dense query supervision pairs, sampled randomly or uniformly in a predefined bounded space. With the development of diffusion models that prove powerful in generation, especially given large amounts of data for training. Some methods use 2D diffusion models to generate multi-view images and then perform 3D reconstructions from these views. Another approach simplifies this process by extending 2D diffusion into 3D, by iteratively denoising noisy 3D points or voxels under given conditions to conduct reconstruction. Our motivation is to improve the intensive learning paradigm in MCC-style methods with an adaptive query sampling, which aims to sample queries according to the target object shape to allow higher learning efficiency. In doing so, we propose to integrate implicit field learning with point diffusion learning. We perceive the query points as a noisy point cloud to denoise. Specifically, a bunch of noisy points are sampled not only for denoising as in diffusion learning, but also as spatial queries for implicit field learning, so that our model iteratively conducts denoising and implicit predicting to recover the target shape under the RGB-D condition. In this process, the sampled points can gradually get close to the true object shape through denoising, so that it can conduct implicit field learning more efficiently by attending more valuable local regions near the object surface, thus also capturing the fine shape details more easily. Further, we propose a novel self-conditioning mechanism, which leverages the predicted implicit values to reversely assist the diffusion learning. Specifically, we predict the unsigned distances of all noisy points away from the true object surface and employ them as the guidance of noise prediction to condition the denoising. Therefore, the implicit field learning also benefit the diffusion learning, thus forges a cooperative system. In this section, we take a closer look at the methodology. At first, we introduce some preliminaries. Denote the input image and partial scene point cloud as INP, and the point cloud ground truth as X. Given some queries Q in the space, an implicit field model F is required to learn the mapping from Q to the GT implicit value mu. A diffusion model G adopts another kind of learning paradigm, where a noise epsilon and a time step t are first sampled to construct xt by adding the noise into X. Then the model G aims to predict the noise in xt given P and I as condition. In our proposed IPoD, the implicit field learning and diffusion learning are conducted simultaneously, where the query Q is viewed as an explicit point cloud xt for denoising, and the model H aims to predict the noise in xt and the unsigned distance value at each point in xt. This figure illustrates the pipeline of the proposed approach. The input INP are first fed into two encoders to extract features. Xt also goes through an encoder with the sampled time step t. With their features obtained, we fuse them and use two decoders to separately predict mu and epsilon. In doing so, we first predict mu and use it as the self-condition to predict epsilon. At the inference time, given the condition INP, we first sample a pure noise point cloud as xt, then predict the noise to update xt into xt1, and finally obtain x0 as the final point cloud output. These two figures show the implementations of our IPoD, where we provide two kinds of implementations based on transformer and PVCNN, respectively. More implementation details are provided in our paper. We further introduce the experiments to validate the effectiveness of the proposed method. We first visualize the denoising process in this figure. The grayscale of each point indicates its predicted distance away from the target object surface, the darker the smaller. It can be seen that the adaptive queries well capture the target object shape in a progressive manner. The quantitative results on the CO3DV2 dataset demonstrate the superiority of our method, which significantly surpasses other SOTA methods in both reconstruction accuracy and completeness. In the following figures and tables, we use RS1 to refer to the implementation based on PVCNN, and RS2 for the one based on transformer. Here are some qualitative comparison between IPoD and other SOTA methods, which also demonstrate the superiority of IPoD, especially when implemented with transformer. Reconstruction results on the MV ImageNet dataset also demonstrate the superiority of the proposed method, as shown in the figure above. Here are some other qualitative results on CO3DV2 dataset. More visualization results and ablative analysis are included in our paper. Thanks for your watching. If you are interested in our work, more information can be found from our project page and the homepage of GapLab.